Hello. Today's topic is going to be the Claisen rearrangement. It fits in with our continued discussion on 3,3 sigmatropic rearrangements, carrying on from the Cope rearrangement covered in the last episode. A general Claisen rearrangement is shown over here. It's a thermally driven pericyclic reaction involving the conversion of an ether functionality to either an aldehyde or a carboxylic acid, amide or similar functional group containing this keto group. When considering how the rearrangement is going to take place, we're going to focus on looking at the transition state in terms of how it can be stabilised or destabilised, which can influence the stereochemistry of the products. Now, what's not today's focus is the Claisen condensation, which is a lot more well known. It's probably one of the first name reactions that you get taught in organic chemistry, and we'll probably cover it in a future video. But for today, it's all about the rearrangement reaction. So to recap the previous episode, the Claisen rearrangement is a 3,3 sigmatropic rearrangement, and it proceeds via an intermediate that brings together two 3-atom radical-like intermediate species, shown here in this central transition state. Given we're dealing with 3 p orbitals and 3 electrons within that pi system, our highest occupied molecular orbital is here with a single electron populating this psi-2 arrangement of the orbitals, where we have a node in the centre and 2 oppositely aligned p orbitals at either end of our 3-atom chain. That means to bring together the two 3-atom halves of the reaction in such a way that the orbitals overlap, they need to be arranged in this chair configuration so that the mismatched p orbitals on the ends overlap with their counterparts on the opposing side. There are 2 options for doing that. We have the chair conformation here, or we can flip this side and create a boat conformation. This chair conformation is going to be preferred simply because it's less sterically demanding than the boat counterpart shown down here, where we've got this additional interaction between the nodal points of the 2 halves. And for a simple model, we can compare the same situation that we see for cyclohexane. If we look at the relative Gibbs free energy of the 2 forms, chair conformation is the lowest energy, whereas the boat conformation is higher in energy by 5.3 kcal per mole. Looking at these 2 transition states for the Claisen rearrangement, we can see that the chair, again, lowest energy transition state, and while the boat is a viable arrangement of orbitals, for the rearrangement to proceed, it is higher in energy by 5.8 kcal per mole, making the chair transition state the preferred conformation for the reaction to proceed. Here is a look at the thermodynamics of the Claisen rearrangement. Here we can see the archetypal reaction. Bond in red is to be broken, bond in blue forms once the rearrangement is complete, and we can change the identity of the atom adjacent to this keto group. If we consider the simplest form, where X is a hydrogen atom, we can see that once the rearrangement occurs, the product form is lower in energy than the starting material, so the reaction is energetically favourable, but the energy barrier to adopt the transition state is about 30 kcal per mole. If you, however, change X to be an alcohol or an amine, meaning the product is going to be a carboxylic acid or an amide, this has 2 effects on the reaction. The first is the reaction itself becomes even more energetically favourable, so you're liberating 30 kcal per mole once the products are formed, but also the activation barrier has dropped to get us to the transition state. So effectively changing X to be an oxygen or a nitrogen, the reaction proceeds more easily and is more energetically favoured. So in general, what's the appeal of a Claisen rearrangement compared to, say, something like an SN2 reaction, which could generate the same desired product shown here in the centre? Well, benefits of the Claisen over an SN2 reaction is the Claisen is an intramolecular process, which typically means you have more control and less byproducts. You have 100% atom economy for the reaction, but probably the biggest benefit is you gain more stereo control. So there are various factors that you can take advantage of to impart diastereo selectivity on the products. Our first example to highlight the complexities of the Claisen rearrangement is aryl-allyl ethers. We can see here the archetypical Claisen rearrangement, with the bond to be broken highlighted in red, bond to be formed highlighted in blue, and by numbering the atoms moving away from the bond to break, we can see it's a 3,3 sigmatropic rearrangement where the electron density migrates from the 2,3 positions over to the 1,2 positions. This gives us our ketone group, making it a Claisen rearrangement. Now, one thing you'll notice is that we've gone from an aromatic ring to a non-aromatic system in the product. However, given that we've formed a ketone group, one thing we can do at this point is enact ketoenol tautomerism, and that can reform our aromatic ring. Essentially what this does is it gives us our true product, which is a phenol with a terminal alkene side chain in the ortho position. Okay, so relatively simple. Let's look at a slightly more complicated example. Similar starting material, but this time we've got 3 methyl groups placed in the ortho ring positions and appended to the alkene chain. Once again, we can identify the bond that's going to break, we can redraw the product showing the bond that's going to form, and this gives our product for the Claisen rearrangement. But one thing we might be wondering at this stage is what's the stereochemistry on these 2 methyl groups, as we're essentially creating 2 new chiral centers. And to answer that question, we need to visualize the transition states for our Claisen rearrangement. Now, one thing we know is that the transition state is going to adopt a chair conformation, so we can draw that in. I've done this by placing the oxygen at the bottom, sort of anchoring the chair, drawing in the bond to break, bond to form, and the intermediate double bonds here. As we know, it's a pericyclic reaction, so all these bonds break and form simultaneously. And the final step we need to do is we need to add the methyl groups into the correct positions in the transition state. Now, the way to do this is we look at the starting material, specifically at the double bonds, and we assign the methyl groups into either a cis or trans configuration. For our lower double bond, we can see that our methyl group is cis in relation to our oxygen. For the top double bond, we can see that the methyl group is in trans configuration. What we need to do is to now relay that information into our transition state with our oxygen at the bottom. For the methyl group to be in a cis configuration, we're going to place it downwards in the axial position, recreating this cis conformation. Whereas for the top double bond, we're going to have to put our methyl group in an axial position to recreate this trans configuration that we see in our starting material. Once we've done that, we can see the location of the methyl groups in relation to one another. So in this particular transition state, we can see that the hydrogen groups are on the top, the methyl groups are on the bottom. So both methyl groups will be arrayed in the same direction. We can draw that out down here. So our 2 methyl groups in the product, they're going to be arrayed in the same direction, so they're drawn coming out towards us. Now, another thing you should know is that you can draw chair configurations in this orientation, but you can also draw the mirror image of that same chair configuration like so. So effectively, once you've created this transition state, you can mirror it to create the other transition state. What this will do is essentially create an enantiomer. So if this is one of our options for the product, we need to also include the enantiomeric form of that product, where the 2 methyl groups are still both arrayed in the same direction, but they're pointed away from us. Now, going forward, we're only going to focus on one of these enantiomers, but be aware that both would have an equal likelihood of forming in this situation. So we've drawn out one of our intermediate products, but if you watch the previous episode, you'll see that this arrangement of methyl groups shown here and this positioning of 2 double bonds between the 2,3 positions are primed to undergo their own 3,3 sigmatropic rearrangement. This time there's no ketone group to form, so this is going to be a cope rearrangement. And once again, knowing our location of the bond that would break, bond that's going to form, we can redraw out our second intermediate product based on undertaking a sequential Claisen followed by a cope rearrangement. Now, if you were to do this experimentally, this would be the major product that you would see with trans conformation of the double bond. However, there would also be a minor product whereby this side chain, shown in pink, would be in the cis conformation. And the ratio of conformers would be 6.7 trans to 1 in the cis conformation. And seeing as we're on a roll, we may as well have a look at why that is. So for the major product, where we're going to generate a trans double bond on the side chain, we need to draw out our chair transition state once again. Here's our starting material. We can see our bond that's going to break highlighted in red. We've drawn out our chair configuration for the transition state, making sure we retain the correct stereochemistry at this position shown here. And when we redraw out our product, we form our new bond highlighted in blue, and this gives us our trans olefin as the major product. So what about the minor product? Well, for a cope rearrangement, the chair conformation is the main product that you see, but there's also possibility of a boat transition state being seen. We can draw that out by basically changing the orientation of the terminal alkene, giving us our boat transition state. And if we redraw our product over here with our bond forming highlighted in blue, when it's in this configuration, we can see we wind up with a cis alkene side chain. And to reiterate, boat transition state, more sterically constrained, less energetically favourable, so we see it as the minor product, whereas the chair transition state minimises these energies, so we see this as the major product. So back to our reaction scheme, we've covered the Claisen rearrangement, we've covered the cope rearrangement. This gives us our second intermediate product, but once again, we've lost the aromaticity of our ring by imparting a ketone group. We once again have a situation where keto-enol tautomerism can be implemented to recreate our aromatic ring. And once we do that, we get our final major product shown here. Once more, it's a phenolic compound where our side chain has migrated to the ortho and then finally the para position where it stays. So given Claisen rearrangements have interesting stereochemistry that you can harness, it's worth knowing how you can influence that stereochemistry. Now let's say you have a starting material that resembles this. The stereochemistry of the products is influenced by the stereocenter of the functional group that is migrating. So here that stereocenter is highlighted in red. That stereocenter is what guides the stereochemistry in the products. The stereochemistry of this R group doesn't really factor into it. Because the rearrangements occur in this syn fashion, it means that these groups migrate across the molecule, meaning the stereochemistry needs to be retained when this occurs. So to explore this, we can have a look at endocyclic olefins. These are Claisen rearrangements where one of our alkene functional groups is embedded inside a ring. You can see in this material we've got some stereochemistry already embedded in terms of this tert-butyl group, but per the previous slide, the stereochemistry doesn't really matter in this position. But interestingly, there's no stereochemistry available where we're undergoing this sigmatropic rearrangement, and yet we do see diastereoselection, favouring the product where the group migrates into an axial position rather than an equatorial position. To a large extent, nearly 9-to-1. So why would this be if there's no stereochemistry to transmit where the rearrangement is taking place? Well, the first thing we can do is we can draw out our transition state, shown here in the centre, and there are two options whereby the side chain could position itself to undergo the reaction. The atoms partaking in the rearrangement, shown here, could position themselves above the double bond in the ring, which would be our blue R group here, or those atoms could be positioned below the double bond of the ring, highlighted by this green scenario shown here. Now, to know which situation is preferred, we actually need to think back to strained cyclohexanes containing a double bond and the preferred conformation that they would like to take once reaction occurs and that double bond disappears. So essentially in this form, this cyclohexane cannot adopt its preferred chair conformation because it has this double bond locking these atoms into planarity. And we draw that down here. However, once our reaction occurs, that planarity is gone, and the cyclohexane ring, it can adopt the chair conformation that it would prefer. With that knowledge, we can draw the products for each scenario, either the side chain attacking from the top or the side chain attacking from the bottom. If the side chain were to attack from the bottom, we would create this new transition state, and as we can see, it's in this sort of twisted boat conformation, which is higher in energy. So essentially this carbon will move downwards to meet the new R group. This functional group will move upwards, giving us this sort of figure of 8 twisted boat. That's not ideal. The molecule would prefer to react, giving a chair conformation which is lower in energy. If our side chain instead attacks from above, that's exactly what we see. Our constrained cyclohexane loses the planarity of the double bond. This carbon moves upward to meet the R group. This carbon moves downwards because the double bond disappears, and we get this new chair transition state shown here. We can see that our R group is in the axial position, pointed upwards, as we see in our experimental results for our major product. meaning essentially that the diastereo selection has nothing really to do with the Claisen rearrangement per se, but it's instead about the strained cyclohexene adopting a chair conformation over a twisted boat conformation as the reaction proceeds. Just to show you how this side chain would position itself in these two scenarios, I've redrawn it out, highlighting the transition state, trying to show the chair transition state that actually occurs for the Claisen rearrangement itself, not the cyclohexane ring this time. As you can see, attacking from the top or attacking from the bottom, both can form a valid transition state where all the orbitals are correctly aligned to react, but it's the influence of this strained ring that gives us our diastereo selection. You might be looking at this and thinking that the tert-butyl group might offer some sort of steric influence over these transition states, but it's too far away. So as we discussed before, stereochemistry in this position does not really influence the stereochemistry of the Claisen products. So that was a situation where there was stereochemistry away from the Claisen transition state. What if there's stereochemistry within the Claisen transition state? So for this, we can learn some lessons from cyclohexane. Here we have cyclohexane in a chair conformation. We have a single methyl group positioned in the equatorial position, and we can see that it is lower in energy than when the methyl group is in the axial position. Because when the methyl group is in the axial position, there will be some steric clashing with the hydrogens that are also in the axial position. So this conformation is 1.75 kcal per mole higher in energy than when that methyl group is in the equatorial position. Now, if we imagine our cyclohexane in the chair conformation instead as a Claisen transition state, we can understand that if we have a similar situation where we have a methyl group either in an equatorial position or in an axial position, the methyl group in the equatorial position will be lower in energy if all other factors are the same. So what that means is a reaction proceeding by this transition state will be easier to affect than a reaction that proceeds by this higher energy transition state. We would expect this to be a major product while this would be a minor product. So here we have a simple reaction that would showcase this idea. We have our starting material, our bond to break is shown in red. We have two products that we could form. New bond is shown in blue. We identify that the product that has a trans arrangement of the olefin will be the major product, while the product that has the olefin in a cis conformation will be the minor product. And we can justify this by looking at the transition states. So it's the exact scenario we talked about on the previous slide. Here we have our methyl group in an equatorial position. Here we have the methyl group in an axial position. This transition state is higher in energy than this transition state, meaning this transition state is more likely to proceed than this one. Here are some experimental examples. We have this starting material, variations on these functional groups. We have our two expected products, our major product where our double bond is in the E conformation or trans, our minor product where we have our double bond in Z conformation or cis. We get this same 9:1 ratio of E to Z, and you can actually manipulate this ratio by increasing the sterics of this R2 functional group shown here. So for our major product, thinking about the transition state, R2 would be in the equatorial position. Minor product, the larger you make R2, the more of a steric clash it's going to have with the other functional groups in axial positions in that chair transition state. Here we have another experimental example. We have our starting material. X is a functional group that they are systematically changing the sterics of, so increasing the steric bulk of the X functional group. We have the major pathway, where the major product has this E conformation about the double bond. We have a minor pathway where our product has a Z conformation around this double bond. Looking at our two transition states, R2 is an ethyl group, and we can see that when it's in the axial position, if you increase the steric bulk of this X group from a hydrogen to a methyl to a methoxide to a dimethylamine, you increase this steric clash. If, however, our ethyl group R2 is in an equatorial position, it really doesn't matter what you do with this X functional group. It is out of the way and there is not going to be that steric clash. And interestingly, by increasing the steric bulk of X, they were able to effectively eliminate the minor reaction pathway using this strategy. So that's it for Claisen rearrangements. It is yet another 3-3 sigmatropic rearrangement, and I'd recommend watching the episode on the cope rearrangement if you haven't already. The key difference is you form a carbonyl group, or even better, a carboxylic acid or amide group, which drives the reaction forward. However, one of the challenges of recognizing a Claisen rearrangement is that that carbonyl group can then undergo secondary reactions such as tautomerization to reform the aromaticity that was lost, typically giving you a phenol in the product. It's worth knowing that the Claisen rearrangement is highly stereoselective, gives you excellent atom economy, and that it always proceeds through a chair-like transition state. This transition state is influenced by nearby functional group sterics, which imparts diastereoselectivity. That's all for today. Thanks for watching.